Hi. Okay, so welcome to this lecture, which I've entitled Three-Dimensional Vectors and Their Notation for Physics 2010. This is going to finish up section 1.4 in our Matter and Interactions textbook. It covers some more advanced topics on this subject. The last couple of lectures that you've seen on it are more of a review of your 1000 level type physics. And so in this lecture, we get a little bit more into the three-dimensional aspect of it, because in your 1000 level physics, primarily you're doing two-dimensional problems. And we're also going to harp a little bit more on the notation in Physics 2010 than you might have in your 1000 level physics. So let's get started. All right, so first, like I said, we're going to harp on notation. Without proper notation, reading someone else's work or reading through a textbook could be really confusing. And so for this course, we're going to be graded a little bit more harshly for improper notation, and I want to make sure that your notation is correct. To some, this might seem a little picky, but as you go on in your physics studies, say you get into some of the 3,000 and 4,000 level physics courses, it's going to be even more important then. And so it's important to kind of cement those ideas right now. Now, it is true that notation varies from book to book, and that can be super annoying. So what you learn for this textbook might be slightly different from some other textbooks. However, generally, most notation is the same. One really annoying difference, though, I will say, is that some textbooks they use, for example, for unit vector notations, I hat, j hat, and k hat are the ones that you learn about in your calculus-based classes, and that's the ones we're going to use here. But in some other textbooks, they might use, for example, x hat, y hat, and z hat instead of I hat, j hat, and k hat. So some differences like that are to be expected, but I admit that they're kind of annoying. Okay, so regarding notation, as we've already said, when we indicate a vector, what you do is you write the variable name. So for example, a common position vector variable name might be r, right? And then you put an arrow on top of it, okay? So as shown on the slide here, you've got some common variable names. It might be r with an arrow, v with an arrow, and a with an arrow for position, velocity, and your acceleration vectors respectively. So that's some common notation. Sometimes other textbooks might use bold font and things like that, but since it's almost impossible to use bold font on a homework paper, use the arrows, okay? So for your homework, I want you to indicate a vector with an arrow on top of it. If you don't do that, of course, you might lose a point or so. Okay, now, if you're giving the vector components, there's a couple of different ways to do that. And there's a couple of ways the textbook does that. So in Matter and Interactions, they give the x, y, and z components of a three-dimensional vector r, for example. They use these sort of angled or, almost like wedge-shaped brackets to indicate that it's a vector. And so they do that rather than using the regular curved brackets to really emphasize the fact, hey, pay attention, this is a vector here, okay? So that's how Matter and Interactions gives the components of your vector. And of course, it always goes x component, y component, z component in that order. That's the convention. You could put the units inside next to each number, or if you want to save space, you could put them outside the brackets as I did here. So in this position vector, your x, y, and z coordinates are 1.5 meters, 2.7 meters, and 9.3 meters. But rather than write m 3 times, I just put it outside the brackets like here, and that's acceptable too. Either way is acceptable. Now, sometimes we use subscripts to indicate which of the components things are, and also we sometimes just use subscripts in general to sort of differentiate different vectors. So for example, if you had two different velocity vectors, you might call them v sub I and v sub f, for v initial and v final, for example. So subscripts get used a lot. In this example here, the components of the velocity vector v are given as vx, vy, and vz, and that tells you that those are the components in the x, y, and z of that velocity vector, respectively. Now, in the position vectors, sometimes they use, for example, rx, ry, and rz, but then often commonly they also just say x, y, and z for the x, y, and z components of the vector or for the position coordinates. If you've got different types of coordinates, we might use cylindrical or spherical coordinates in this class, for example. Then instead of x, y, and z, you might use r, theta, and z, for example, for cylindrical. Now, another type of notation that's super helpful is the unit vector notation. So if we had a vector 1.5 meters, 2.7 meters, and 9.3 meters for our position vector, for example, then instead of writing it this way with the wedge-shaped brackets, we might write 1.5 meters I hat plus 2.7 meters j hat plus 9.3 meters in the k hat. And here I hat, j hat, and k hat are the unit vectors for the x, y, and z coordinates, respectively. So this should be a review, I hope, for most of you, but remember that the unit vectors, they put a little hat on top, a little caret to indicate rather than an arrow. So for a vector with some length other than 1, you use an arrow on top, but the notation for a unit vector is to use a little caret on top like is shown here, and then they're designated, we say, when we talk about them, we say I hat, j hat, and k hat for the unit vectors in the x, y, and z direction. Now, hence the name, unit vectors all have length 1, okay? So in a standard Cartesian coordinate system with x, y, and z coordinates, you might have a unit vector by 1, 0, 0, 0, 1, 0, and 0, 0, 1, okay? So those are the unit vectors. They all have length 1. Okay, let's talk about a little bit more notation and get a little bit more into this. The magnitude or the length of a vector is a scalar. So you find the magnitude or the length of a vector by taking the square root of the sum of the squares of the components. Now this is pretty easy to see if you're looking in 2 dimensions, right? If you just had x and y components, for example, then the x and y components of your vector make up the legs of a right triangle, and then the length is the hypotenuse of that. And of course you use the Pythagorean theorem to solve for the length of that. But the form doesn't change when you go to 3 dimensions. The length of the vector r, if the legs in the x, y, and z direction are just x, y, and z, it's still the square root of the sum of the squares of the components, which would be, in the case of a 3-dimensional position vector, the square root of x squared plus y squared plus z squared. Speaking about the notation, if you're trying to discuss or find the length of the vector, what you do is you write your position vector, in this case it would be r, and then you write the little absolute value signs on the outside of the vector, and that indicates that you're taking the magnitude, and then it's understood that this is a scalar, okay? Alternatively, sometimes we'll drop the absolute value and the arrow and just write the variable name by itself with no arrow over the top, and that could also mean the length or magnitude of your vector r. Now, you can find a unit vector for any arbitrary vector. It doesn't have to just be I hat, j hat, and k hat. So for example, you could just say I have a vector of length 1 pointing along this arbitrary direction, okay? If you wanted to do that, the way to find your unit vector, I'm going to call it r hat here, would be to take the vector itself, r, and then divide it by the magnitude, okay? So if you do that, then the components of that unit vector would be as given here in this equation. For the I hat, x over the square root of x squared plus y squared plus z squared. For the j hat, y over the square root of x squared plus y squared plus z squared. And then for the k hat, z over the square root of x squared plus y squared plus z squared. So that would be the I hat, j hat, k hat, or x, y, and z components of some arbitrary vector r. So what about that vector that I gave in the example with the components 1.5 meters, 2.7 meters, and 9.3 meters in the x, y, and z directions respectively? Let's double check and make sure that we're working this okay by plugging and chugging into our formulas. So the length of this vector, let's find that first. It would be the square root of the sum of the squares of its components. So that would be the square root of 1.5 squared plus 2.7 squared plus 9.3 squared. Now, when we're all done taking our square root and everything, the units are still going to just be meters, okay? So that's why I put the meters on the outside. I just didn't want to write m 3 times. So when we do that mathematical operation, plugging it into our calculator, we end up with 9.8 meters if I just keep 2 significant figures. Okay, so now plugging into our formula to find what the unit vector r hat might be, I would take that length, 9.8 meters, and put it on the bottom of these fractions, and then on the top I would put my x, y, and z components respectively. So the I hat component would be 1.5 meters divided by 9.8 meters. The j hat component would be 2.7 meters divided by 9.8 meters. And the k hat component would be 9.3 meters divided by 9.8 meters. And then I would have a unit vector of 0.15 I hat plus 0.28 j hat plus 0.95 k hat. This unit vector would point in the direction of our hat. And if you double check me there, if you do the square root of the sum of the squares of 0.15 squared plus 0.28 squared plus 0.95 squared, you'll see that you get 1, or close to it with rounding error, since I did truncate to 2 sig figs for each one of those numbers. Okay, also note that you can write any vector as the length or magnitude of the vector times its unit vector. Okay, so we could write vector r as the magnitude of r times r hat, where r hat would be that unit vector, like I found in this previous example. Now, let's look one more time and think a little bit harder about this arbitrary unit vector r hat. If you look at each one of those things, you can see that your components of your unit vector are actually the cosines of the angles of each one of those of the vector with respect to each one of the x, y, and z axes. This is a little easier to see if you look at figure 1.28 from your textbook, which is shown there on the right. So here we see an arbitrary vector r indicated by the arrow there in purple. And then you can see that if you look at each one of the components there, right? So if you had r sub x, which would just be x here, and then divided by the length of the vector, well, that's the definition of your cosine, okay? So the cosine of the angle with respect to the x-axis, which I call theta x here, cosine of theta x is the component of your r hat unit vector in the x direction, okay? Likewise, cosine theta y would be y over the square root of x squared plus y squared plus z squared. And cosine of theta z would be z over the square root of x squared plus y squared plus z squared. Theta x, theta y, and theta z are the angles of the vector with respect to the x, y, and z axes. And that's indicated over here in this figure, right? As you can see. You might need to pause the video for a second and really stare at that to make sure that you understand it, okay, before moving on. After a little bit of study, though, I think that you'll see that that's true. Now, we call these cosines the direction cosines, okay, for obvious reasons. So let's go back to our little example that we had before with our vector with the 1.5 meters and so on and so forth components that we just did, and we just found the unit vector for. So remember that our unit vector for that vector was 0.15 I hat plus 0.28 j hat plus 0.95 k hat. Okay, so those are our direction cosines. Now, using our inverse or arc cosine function on our calculator, we can see that if you solve for those angles, for the theta x, you would get 81 degrees. So that would be the inverse cosine of 0.15. For the inverse cosine of 0.28, you get 74 degrees, and that's the angle that that vector makes with the y-axis. And then if you do the inverse cosine of 0.95, you get 18 degrees. So that's the angle that that vector makes with the z-axis, okay? Now, you might be staring at that thinking that it doesn't quite make sense. And there's an example in your textbook. Let's see, what example number is it? It's the example on page 16 there. They give you an example, which I think you should look at. It's shown in figure 1.30. If you look at that example, then you might be led to imagine that there's always going to be a really neat relationship, a really simple or straightforward relationship in between those angles. But be careful, that's not the case. As you can see here, if you look at the angles 81 degrees, 74 degrees, and 18 degrees, there doesn't seem to be too much rhyme or reason or mathematical relationship between those three angles. And that's typical of a regular three-dimensional vector. There's not going to be a simple relationship in between the angles. Now, if it were just a two-dimensional problem and the vector just lie in the xy plane and didn't have a z component, then of course the angle with respect to the x-axis, right, plus the angle with respect to the y-axis would be summing to 90 degrees, right? I mean, if you draw that picture, it seems pretty straightforward. But in 3D, there's not going to be that simple relationship, okay? It's not going to add or subtract to give you 90 if it's just some arbitrary three-dimensional vector. So I wanted to do this example so that you wouldn't have that expectation, okay? All right. Well, I hope that gets you started on notation and three-dimensional vectors. Be sure to read section 1.4 in your textbook now. The three lectures that I have given and summarized here will cover the topics of graphical and component vectors, component vector addition, and graphical vector addition, the definition of what's a vector, and then how to handle a three-dimensional vector, and emphasizing a little bit on the notation. So section 1.4 is a very meaty section. So I do recommend that you definitely read that section. Look through the examples that are given in the textbook in addition to the examples that I do in the online lectures. Don't just rely on me, okay? All right, see you around.